now we can talk about the actual electrochemistry. So electric current is a flow of electrons, movement of negative charges. And so this can be through a wire, or it can be ions moving through a solution, still electric current. Redox reactions can generate electrical current because they generate electrons, right? They transfer electrons from one thing to another. So if we look at zinc metal with copper ions, zinc has a greater tendency to lose electrons than copper does, and so zinc is going to transfer its electrons to the copper ion. So there is a transfer of electrons. In a solution where these two are in contact, the zinc becomes a dissolved zinc ion, and the copper gets deposited on the zinc as solid copper. So electrons have been transferred from the zinc to the copper. I'm getting ahead of myself. We'll look at this picture first. So a strip of zinc metal, and you put it in a copper sulfate solution where there's copper 2 ions, and that's why it's this pretty blue colored. What happens is the zinc atoms will give 2 electrons to the copper ions, making the copper ions into copper atoms and the zinc atoms into zinc ions. So the zinc dissolves and the copper deposits onto the zinc, and so you get this black furry looking stuff that is copper depositing kind of not very attractively on the zinc. Okay. If we separate the zinc atoms and the copper ions, electrons can still move, but we can force them to go through a wire instead of just going directly. And so we can use that chemical reaction to generate electric current. So we do this in an electrochemical cell. So this is a device in which a chemical reaction is occurring, and it's either that the chemical reaction is spontaneous and is producing electric current, or the reaction is non-spontaneous and we are using electric current to cause the reaction to happen. You can do it either way. So a voltaic cell, also called a galvanic cell, is when electrical current is produced from a spontaneous chemical reaction. An electrolytic cell is where you use electrical current to drive a non-spontaneous chemical reaction. Okay. Galvanic, voltaic versus electrolytic. Okay, so here is a schematic of a voltaic cell. This is using the same reaction we were talking about. So we can take that chemical equation and divide it into 2 half reactions. So zinc going to zinc ion would release 2 electrons. If we had copper going to copper ions, that would also release 2 electrons. These are both written, oxidation is loss of electrons. These are both being written as oxidations. So the zinc is being oxidized, the copper is being oxidized. But we could take either of those and reverse it and write it as a reduction. So here's the oxidation reaction, zinc going to zinc ion plus 2 electrons. The reduction that's occurring is the copper ion plus 2 electrons to make solid copper. So what we've done now is we've separated the 2 half reactions. So over here we have zinc metal and a solution containing zinc ions. And on this side we have a strip of copper metal and a solution containing copper ions. So on the zinc side, the zinc is releasing zinc ions, and the 2 electrons that came from that, they can't be transferred directly to the copper. They're going to go up through the electrode and through the wire and through the light bulb and through this wire and over to this copper electrode. At this copper electrode, the 2 electrons that are coming over from the other side are given to a copper atom, which becomes a copper ion. And so the chemical reaction is accomplished. The zinc is being oxidized, the copper ion is being reduced, but we force the electrons to travel through a wire and do something for us, like the light bulb. So the strips of metal here are called electrodes. Each side here is called a half cell. There's a half reaction occurring in each of the half cells. The chemical reaction will also occur if we put it all together, but then we can't benefit from the movement of the electrons because they just go directly from the zinc to the copper, and we can't get them to do anything for us. So by separating them, we can get them to flow through the light bulb and give us some light. Yes?
What's the purpose of the salt bridge?
That's an excellent question. What's the purpose of the salt bridge? So if these were not connected, and we had electrons moving from the left to the right, then we get a buildup of negative charge on this side. And nature doesn't like to do that where it separates charges, and so the reaction would stop very quickly. So what we need to do is we need to allow negative charge to return to the other side. We're not going to do it with electrons, though. We're going to let the counter ions, the negative nitrate ions that are also present, we're going to let those move through this salt bridge. And potassium ions can move to the right, and so that'll maintain charge balance in the cell. The salt bridge, there's different ways to make salt bridges. One is to just make a glass tube full of sort of like a gelatinous, like an agar solution or something, and it's saturated with something non-reactive like potassium nitrate. And then you've got some sort of a porous plug, here it's glass wool, that's going to allow ions to go through, but it's not going to let all of this come out and mix with the rest of the solutions. The reaction is spontaneous because zinc has a greater tendency to ionize, and so its equilibrium lies further to the right, and copper has a lower tendency, and so it's going to lie more to the left. So the zinc electrode becomes negative with respect to the copper electrode. This is called the anode. That's the negative electrode, and this is the cathode. Any other questions? Yeah, so I kind of already covered some of this stuff. So if the half cells are connected by a wire, we get spontaneous flow of electrons from the zinc to the copper. The zinc ion equilibrium shifts to the right, oxidation occurs. The electrons flow into the copper and cause that equilibrium to shift to the left. So we're looking at this equilibrium shifting left. We're adding electrons, and so that causes this reaction to go to the left. We're writing it here as a reduction. So, any other questions? So we can think of electrical current as being a lot like flowing water. It's really hard to think about how electrons move, but we understand how water works, right? Probably have all played with a garden hose as a child and squirted yourself in the face and then delighted in squirting other people and get really wet and then mom gets mad. So the rate of electrons flowing is like the rate of water moving. So of course we have to measure the electrons, right? If we think about water moving, why does water move? Like, why does water come from Pine Flat over the dam and down the Kings River? Why does it flow that way? Why doesn't it flow the other way? Gravity, right? Gravitational potential energy, right? We are lower here than up at Pine Flat, and so water flows downhill, right? That's what it does. So that water current is driven by a difference in gravitational potential energy. Electric current is driven by a potential difference. Potential difference is a measure of the difference in potential energy per unit of charge. So we measure electrical current using a unit called an ampere. Abbreviation is capital A. It's often called amp. Coulomb is a unit of electrical charge. And so an ampere is 1 coulomb per second. It's how many electrons are moving per second. A coulomb happens to be equal to 6.242 times 10 to the 18th electrons. And so it's that many electrons moving per second is 1 amp. That current is driven by a difference in potential energy, and we measure that using volts. Abbreviation is capital V. A volt is 1 joule per coulomb. So let's explore this analogy. If we have a large potential difference, then the electric current is going to flow very strongly. It's going to be fast, right? A large difference in charge, we've got a strong tendency for the electrons to flow. It's like a steeply descending stream bed. So when this is descending steeply, the water is very vigorous in its movement, right? So another word for potential is electromotive force, or EMF. Another term for the potential difference, that's the force that results in the motion of electrons. If the difference in potential is large, then the electrons move with more force, more electrons move. So the cell potential, E cell, or the cell EMF, is the potential difference between the two electrodes in a voltaic cell. It's a little bit like looking at a portion of a stream and saying, well, what's the difference in elevation between the beginning and the end? If the difference in elevation is really big, that stream's going to be moving really fast. If it's just a teeny tiny bit different, it's going to be moving slowly. And if it's the same, if there's no difference, then you call it a lake, right? Because nothing's moving, it's just sitting there. So cell potential tells us what direction the electric current is going to move and how strongly it's going to move. So the cell potential depends on relative tendencies of the reactants to undergo oxidation and reduction. So if you have a substance with a high tendency towards reaction, combined with a substance with a high tendency towards reduction, then you get a high potential on your cell. Of course, it's also going to depend on concentrations and temperature. So what we call the standard cell potential, E cell with the 0 there for standard, that's going to occur at concentrations of 1 mole per liter or pressures of 1 atmosphere. So that's that same definition of standard that we've used for other things. So in that cell that we just looked at with the copper and the zinc is, has a tendency toward losing its electrons, and the copper, compared to the zinc, has a greater tendency to accept electrons. And so the standard cell potential here is, bless you, 1.10 volts. If we put nickel in here instead of zinc, nickel does not have as strong of a tendency to be oxidized, and so the cell potential drops to 0.62 volts. So this would indicate that it's not as spontaneous in the forward direction. If the cell potential is negative, it means that the current's going to flow in the opposite direction. So if the head of your stream is lower than the ending of your stream, it's going to flow backwards, right? So, as with many things in chemistry, we've got pairs of things that we have to remember how to match up. Oxidation occurs at the anode, reduction occurs at the cathode. So I've always had trouble with that. What makes sense to me is that oxidation and anode both start with vowels, and reduction and cathode both start with consonants. Or you can also think about a red cat. So reduction occurs at the cathode, oxidation occurs at the anode. The anode is more negatively charged. That makes sense to me because anions are negative. Right? The cathode is more positively charged. Cations are positive. So electrons are flowing from the anode to the cathode because the electrons are coming from that negative anode. Electrons are negative. And they're like, we're repelled by you, negative electrode. And down the wire, they see this positive electrode, and they're attracted to that. So electrons flow from the anode to the cathode. And you probably have to label some things on a diagram on the exam, and so you have to keep these things straight. And if I was doing it, I would talk through it like I just talked to you right now. I think that works better than trying to memorize it. So this is where we get to why we need that salt bridge. So if we only had electrons flowing from the anode to the cathode, we get a buildup of charge. And that's going to cause the reaction to slow down and stop. So we use a salt bridge. That allows the counterions to flow between the half cells without allowing the solutions to mix. Because if we let the solutions mix, then the electrons aren't going to go through the wire anymore. So we can use an inverted U-shaped tube with a strong electrolyte in it to connect the two half cells. So the negative ions in the salt bridge are going to flow in a direction to neutralize the accumulation of positive charge at the anode. And the positive ions are going to flow to neutralize the negative charge building up at the cathode. So here's that cell again. So the anode is negatively charged, and the electrons are going to leave the anode and go towards the cathode, which is positively charged. Reduction is occurring at the cathode. Reduction is an increase or a gain of electrons. And so the copper in this electrode is gaining, at this electrode, copper ions from the solution gain electrons and become copper solid. And so they add to the the cathode. Oh, good grief. Over here, the zinc anode is undergoing oxidation. It's losing electrons, and so it's generating zinc ions in this solution. So over here, we're going to get zinc ions building up in the solution. Got electrons moving this way, and this is going to get a buildup of negative charges because the copper ions are becoming copper atoms, and then we've got nitrate ions that are left in solution. So the nitrate ions can move towards the anode to neutralize the charge. Potassium ions that are in the salt bridge will move to the other side. There aren't any potassium ions in here, but zinc ions can start going up in here, and the potassium ions go over there. And the charge balance can be reestablished. Any questions? So instead of drawing pictures like that all the time, we have line notation. And we need to understand what this line notation means. So over here we have the oxidation half reaction. Zinc is losing electrons and going to zinc ion. And on the right side we have the reduction reaction, and that's just convention. Here we have the copper ions gaining electrons to become copper metal. So the two parts of the oxidation and the two parts of the reduction are separated by a single line. And then there's a double line between the two half reactions that kind of represents that salt bridge. So these are on one side and these are on the other side, and the salt bridge is in the middle. So the single vertical lines are separating different phases. The zinc is a solid, the zinc ion is aqueous. The copper ion is aqueous, the zinc copper is a solid. if you have reactants and products like the copper ion and the copper solid that are in the same state, which can happen, maybe they're both aqueous, instead of a line, you're going to use a comma. If we end up with all of the species in the half reaction being aqueous, we have to use something for an electrode, because you can't hook a wire onto these ions in solution, and you have to be able to hook a wire onto something in there. So you use an inert electrode, a metal such as platinum that's not going to react, but just allow be a place where the electrons can get transferred. Okay, so here's an example of a redox reaction occurring in an electrochemical cell. This one's already been balanced for us. Here's the line notation down here. What this is telling us is that we've got oxidation occurring here, iron and iron 2 ions, and on the other side, on the reduction side, we've got permanganate ion, hydrogen ion, and manganese 2 ion. Those are all aqueous, and so they're separated with commas. None of them are solids. And so we've got platinum here as the electrode. That could be gold or palladium or anything that's not very reactive. So let's write the oxidation and reduction half reactions for this cell. So this is the oxidation. So we've got iron going to Fe2+. So we got 5 Fe solid going to 5 Fe2+ aqueous. What's missing from that? Electrons? And oxidation is loss of electrons. So we should have electrons as products. And the chart is going to tell us what those should be. I think that's Mr. Balo doing something fun in physics. So we need how many electrons over here? 10. 2 times 5. 10 electrons. Then the reduction is going to be the permanganate ion and the manganese. And I'm going to leave some space there because I know I'm going to have to put some electrons on the left side because reduction is gain of electrons. So I've got the 2 permanganate ions, and I've got the 16 hydrogen ions, and then I've got 2 manganese ions and 8 water molecules. Why did I put the hydrogen and the water with the reduction half reaction? We're all distracted by the fun noises coming down the hallway. Hopefully there won't be any lights flickering and screaming. You're playing with electricity. We're just talking about electricity. Why do these need to be down here instead of up there?
Because the hydrogen is getting
Because this has oxygen in it. This is beautifully balanced without any oxygen or hydrogen things, right? So we don't need that up there. If we were balanced, if we were given this as an unbalanced reaction and went through the steps and balanced it, we'd end up with 2 half reactions, and we would have gotten the H2O and the H pluses in here through the balancing process. So what's missing from my reduction? Electrons. So on the right side, 2 plus 2, 2 times 2 is 4. 2 plus 2 is also 4, but that's not what we're doing. 2 times 2 is 4. Plus 4. And then over here, I've got plus 16 and minus 2, so that's plus 14. Plus 4, plus 14, so I need 10 electrons. It's not a coincidence that this is 10 electrons and that's 10 electrons. So this is our oxidation half reaction, this is our reduction half reaction. The line notation is describing the oxidation between solid iron and iron ions in solution. And over here, the reduction is occurring all in solution with the platinum electrode here to provide the electrons from the wire. So we've got permanganate and hydrogen and manganese. The water here is just the water. That's just the solvent. Any questions? So here is a drawing of that cell. There's our iron anode with iron ions in solution. Electrons are leaving the iron, resulting in iron ions being produced. The electrons come through here, light up our light bulb, come into the platinum cathode, where they can be taken by the permanganate ion and formed into manganese ions. Now here, the oxidation and reduction reactions are in their lowest balanced state, right? Lowest, where's my pointer? Come back. Down here, it's iron to iron 2. We don't have 10s in front of those, right? Any questions? Yes?
What's the function of the salt bridge?
The function of the salt bridge is to allow negative ions from this side to travel over here. Otherwise, we get a buildup of negative charge here and positive charge here, because our electrons are leaving this beaker and leaving behind positive ions. Electrons are coming into this beaker, creating an excess of negative ions, and so then that would cause the reaction to stop. So this allows those counter ions to move back and forth and equalize that. Any other questions?